Yes, thank you for the invitation and for this extremely accurate introduction. So I'm going to talk about the use of spectral methods for the design of graph decomposition algorithms, and also to prove theorems about structures of graphs based on linear algebraic methods. So spectral graph theory is the use of linear algebra in graph theory and graph algorithms. So the starting point is how to think about graphs in terms of matrices, and the most natural way of doing so is to look at the adjacency matrix of a graph, the one that has a row and a column for every vertex and has the weight of the edge uv in the position uv. And for already for this matrix, although I will define a different one that is more useful in some applications, there are some connections between the numerical values of the eigenvalues of this matrix and purely combinatorial properties of a graph. And many of those connections are proved constructively in such a way that also if you're given the eigenvectors of this matrix, you can use them to design graph algorithms that solve various purely combinatorial problems, exactly or approximately as the case may be. So let me state sort of the first result in spectral graph theory, which is already fairly surprising if it's the first time that you see it, and then I will state several recent generalizations of those kind of connections. Okay, so given a graph, we'll define a matrix that is sort of like the adjacency matrix. There is just some normalization that makes its eigenvalues nicer. So here, I is the identity matrix, A is the adjacency matrix, D is a diagonal matrix whose entries are the degrees of the vertices. And this normalized version of the identity matrix is called the Laplacian of the graph. And by definition, if the graph is undirected, this matrix is symmetric and has real valued entries. So in this case, it means that all its eigenvalues are real numbers. If the graph has n vertices, this is an n by n matrix, so it will have n eigenvalues, not necessarily distinct. Now, if we count them with multiplicities and order them, one thing that follows immediately from the definition is that all the eigenvalues will be between 0 and 2. So one of the reasons for this normalization is to always get this fixed range no matter how big is the graph or no matter what the degree of the graph is. And so here are the first non-trivial but already very interesting connections between eigenvalues and combinatorial properties. So the smallest eigenvalue of this matrix is always 0, but it could be repeated. And it turns out that it's repeated exactly as many times as the number of quantity components of the graph. So something that is really purely combinatorial, whether the graph is connected or if not, how many connected components it has, shows up as the number of times that 0 is an eigenvalue of this matrix. And on the high end, all eigenvalues are at most 2, and 2 is not necessarily achieved, and it's achieved only if and only if the graph is bipartite, or in case it's disconnected, if at least one of its connected components is bipartite. So these most basic combinatorial properties, connectivity and two-colorability, are captured by the values of these numbers. So just to give a couple of examples, if I take some graph, compute the Laplacian matrix, compute the eigenvalues of this Laplacian matrix, and tell you that these are those, without knowing anything about the graph, just looking at those numbers, you can say, well, this is a graph that has 10 vertices, because there are 10 eigenvalues. It's connected, because 0 appears only once, and it cannot be bipartite, otherwise 2 would occur as an eigenvalue. So, and that was the graph of which those are eigenvalues. There isn't a kind of unique, the same set of eigenvalues can be had by non-isomorphic graphs, but in this case, this was the graph that I started from. Okay. Say that I took some other graph and I computed the eigenvalues, tell you that they are those. again, there are a few interesting things you can say about the graph. It has 8 vertices. It's not connected. However, it has exactly 2 quantity components, and neither of those 2 quantity components is bipartite. So that was the graph that I started from. Okay, so one last example. If I tell you that I started from some graph and I computed those eigenvalues, you can say this is a graph that has 8 vertices, it's connected, and it's bipartite. And that was the cube. Okay, so how can there be a connection between eigenvalues that are solutions of equations of the form mx equals lambda x to purely combinatorial properties? Well, there is a view of eigenvalues for the case of symmetric real-valued matrices. That is that eigenvalues of matrices are solutions of optimization problems. And once you take this view, since also many graph problems are solutions to optimization problems, one can see that maybe those two concepts are not so far away from each other. Okay, so the characterization of eigenvalues as optimization problems is that for every vector x, so is a vector has one entry, it is the same dimensionality of the matrix. You can consider this rational function. It's the quadratic form summation over ij of mij xij scaled by the norm square of the vector, so that all vectors on a line have the same value here. So the smallest eigenvalue of a matrix is always the minimum of this quantity over non-zero vectors. And in general, the kth smallest eigenvalue of a matrix, it's the solution of this min-max problem. And the way to think about it is to say that the kth smallest eigenvalue of a matrix is small, provided that you can find many different ways of making this quantity small. Specifically, you can find a whole k-dimensional space of ways of finding solutions x for which this ratio is small. Conversely, if lambda k is large, it means that in every k-dimensional space, there has to be at least one direction in which this ratio has to be large. So the relation to quantity components is that for the specific case of the Laplacian, this ratio, okay, so there is a bit of lying in this equality, although the rest of the slide is kind of literally true. But this ratio has a very nice interpretation, which is if you think of an n-dimensional vector as a way of assigning a real number to every vertex, then this ratio is so the variance of this quantity along edges scaled by how big those numbers are. So to make this quantity small, you have to find assignments of real numbers to vertices that don't change very much along edges. And although you can see that if you've seen the other definition before, if x is Boolean, this ratio is the expansion of the set of which x is the indicator vector. So this has already a very concrete interpretation in terms of graph properties. And so the eigenvalues of the Laplacian satisfy this property that lambda k of the Laplacian can be small if and only if there are k-dimensionally many ways of assigning real numbers to vertices so that those values don't change very much along edges. There are lots and lots of ways fundamentally different from each other to assign real numbers to vertices so that don't change very much along edges. Yeah. Now think about the extremal case. All those quantities have to be greater than or equal to 0 because they are sums squared both in the numerator and in the denominator. And 0 is achievable because if you take a vector that is constant on each quantity component, then all the differences in the numerator cancel out, and so you get 0. But that's the only way of getting 0. The only vectors x for which this ratio is 0 are vectors such that for every edge, the value that x gives to the two endpoints of the edge is the same. So it also means that for every path, the value that x gives to all the vertices in the path is the same. So that also means that for every quantity component, the value that x gives to all the vertices in the quantity component is the same. So this quantity is 0 if and only if x is a vector that is constant on quantity components. And now you can already see that if the only solutions that make this 0 are vectors that are constant on quantity components, the only way that it can be the dimensionality of the choices that you have to do that will be the number of quantity components. Because your only degree of freedom is to say which different fixed value there is going to be in each quantity component. So that explains why lambda k is 0 if and only if the graph has k quantity components or more. So let me go through. So in one direction it's clear. If the graph has k or more quantity components, you can pick A to be the space of all vectors that are constant on components, and this is k dimensional. I mean, the other direction is also easy, but I want to give a slightly more roundabout argument, because this more roundabout argument generalizes to much less, to give highly non-trivial results about graph clustering. So I want to argue that if lambda k is 0, that if lambda k is 0, then there has to be k or more quantity components in the graph. So let's look at the eigenvectors of these k eigenvalues that are all 0. So those are k vectors that are all constant on quantity components, and they are orthogonal. So let's define this mapping. This mapping will be interesting in really every graph, not just in graphs where lambda k is 0. It's a mapping that has a lot of useful applications. So I'm going to map, so each of these k eigenvectors, it's a vector that assigns one real number to every vertex. Given k of those vectors, what you have is k real numbers for every vertex. And so you can see this as a mapping of vertices to a k-dimensional real space. For example, for k equal 3, you have these 3 eigenvectors. Each eigenvector gives you a number. For every vertex, you have 3 numbers. So you can see this as mapping the vertices of the graph in a 3-dimensional space. Now, the two observations are one that in the case in which lambda k is 0, this mapping also is constant on quantity components. So that if you look at how this graph is embedded, if two vertices are in the same quantity component, they have to be mapped to the same point in space. And that's because if each of those eigenvectors is constant on quantity components, if two vertices are in the same quantity component, their x1 value is the same, and their x2 value is the same, and their xk value is the same, so the whole k tuple is the same. Okay. So another way of thinking about this is that if lambda k is 0, you compute this mapping, and you see that two vertices get mapped to two different points in space. That means that there is no path between them. They belong to different quantity components. And the other observation is that when I look at how this embedding looks like, where the vertices end up in space, they have to end up in at least k distinct points. Because if they didn't, that would contradict the linear independence of those k vectors. That's sort of just a couple of lines of calculations, easy to see. And so those two things together, they say that there have to be at least k quantity components in the graph. and the eigenvectors tell us what those k quantity components are, because I can just look at the embedding, see what are the distinct outputs of the embedding function, and the preimage of each of them will be a different component. So that's where the fact that those are not just structural theorems, but they also have constructive proofs that give algorithms. Of course, you want to use depth first search, not this, to find quantity components of graphs, but this has much more robustness. So it will turn out that if a graph is maybe not a graph with k quantity components, but a graph with k clusters in the appropriate sense of that, a similar algorithm will recover those clusters, while depth first search will not. Yeah, so what I want to talk about in the rest of the talk are various robust versions of those results. So things that say not what happens when lambda k is 0, what happens when lambda k is positive, but things that say what happens when lambda k is less than epsilon, or it's more than epsilon prime. And to capture even those more approximate statements instead of those extremal statements in terms of combinatorial properties of graph. So I will start by describing what is a robust versions of connectivity, and then we will see that that will capture the cases in which lambda 2 instead of being 0 is small. Okay, so and this notion is edge expansion, or for irregular graphs conductance. It's the following notion. If I have a set of vertices, the conductance of this set of vertices will be the number of edges that leave that set, that have one endpoint in the set and one endpoint in the complement, divided by the sum of the degrees of the vertices in S. So a couple of ways of interpreting this quantity is that if you pick a random vertex in S with probability proportional to its degree, and then you move to a random neighbor, the probability that in this process you get out of S, it's the conductance of S. And another interpretation of this is that the volume of a set of vertices is up to a factor of 2 the number of edges that are incident on that set. The number of edges that have at least one endpoint in S is somewhere between the volume of S and half of the volume of S. So this is saying up to a factor of 2 what fraction of the edges that touch S are actually not entirely contained in S. So small conductance sets are sets where almost all the edges involved in those vertices are inside, very few edges leave the set. If you have a quantity component, its conductance will be 0. So here are some examples that this is a graph whose conductance is 0. This is a graph whose conductance is fairly small. So this is a cut in which the number of crossing edges is only 2, and if I sum the number of if I sum the degrees of the vertices on either side, I get a fairly big number. And that's a graph with a fairly large conductance. Turns out that the best set in terms of ratio of outgoing edges to sum of degrees, it's something like this, and the sum of the degrees is 15, the number of outgoing edges is 5. In a regular graph, the conductance of a set of vertices is also the average over the vertices inside the set of the average fraction of neighbors that are outside the set. So here you see each vertex has one neighbor outside and two neighbors inside. So this fraction is 1/3, which ends up being the conductance. So there are many cases in which if the data of a problem is encoded as a graph, finding small conductance sets is useful. For example, in an undirected social network, a low conductance set of users that are almost only friends with each other. So a set of users of conductance 1/10, a set of users that on average have 90% of their friends inside. And in some clustering problem, it's a useful first step to first construct a graph that has a data item per vertex, and then the presence of an edge means that two items are similar according to some similarity measure. And then low conductance set will be a subset of the data that are much more similar to each other than to anything else. There are actually some divide and conquer algorithms for graph problems. They're based on the idea of recursively partitioning a graph through sparse cuts. In this case, it's important that the cut is roughly balanced. And if those cuts exist, the algorithm can be faster than brute force. Yeah. Now, the reason I introduced this measure is that one can say it characterizes the cases in which the second smallest eigenvalue of a graph is 0. Because lambda 2 is 0 if and only if G has 2 or more quantity components, meaning it's disconnected. And it happens if and only if the conductance is 0. And so one of the classical results in spectral graph theory is that there is a robust version of this connection. So it's not just that the conductance is 0 if and only if lambda 2 is 0, but it's also true that the conductance is small if and only if lambda 2 is small. So those two parameters, this one computable in polynomial time, this one NP hard to compute and conjecturally also hard to approximate, are somewhat good approximations of each other. So there is this quadratic loss, which is known to be unavoidable for some graphs, but at least kind of qualitatively, you see that all the graphs of small conductance are graphs of small lambda 2 and vice versa. And also, it's also important that the proof of this lower bound goes by showing that essentially lambda 2 in the optimization view is a relaxation of the conductance problem. That sort of when you restrict the optimization view of lambda 2 to Boolean vectors, you essentially get the problem of computed conductance. The upper bound is the argument with a non-trivial proof. And it's a constructive argument that says the following. If we have the eigenvector of lambda 2, we can do the following kind of constructive process. Sort the vertices according to the value that they take in this vector. So each vector assigns numbers to vertices. So given the eigenvector of lambda 2, sort vertices according to this. Look at all cuts that you get by taking an initial prefix of the sorted sequence as one set in your cut. Among those n-1 cuts, take the one of best conductance. Well, the conductance of this cut will be at most the square root of 2 lambda 2. So that will say that also your graph has conductance at most this much, but this is a set that you can actually find in polynomial time. In fact, in whatever time it takes to compute this eigenvector plus a linear or nearly linear time computation. And in fact, this algorithm suggested by Fiedler before the proof of this rigorous result so has been in use since the 70s and very often works very well, even better than usually better than the worst case analysis would suggest. So that's one application of these inequalities, that it gives some justification for the performance of the algorithm. But it also has many other applications. The one for which it was originally thought is that it allows you to certify expansions of graphs. So to prove that some graph has large conductance, it's enough to prove that lambda 2 is large. For Killy graphs, it's often much easier to reason about eigenvalues than to reason about expansion. And so the other area in which this result came up originally is that the mixing time of a random walk in a graph is controlled by lambda 2. Graphs where lambda 2 is large, the random walk mixes faster. Often the graphs in which one is analyzing random walks are sort of abstract, exponentially big graphs where there is a vertex for every state of a randomized algorithm, and then the mixing time random walk is like the convergence time of this randomized algorithm. So it can be very difficult to think about what are the eigenvalues of these graphs where there is a vertex for each internal state of an algorithm, and then there is an edge for every move of the algorithm. But it might actually be, in some cases, easier to reason about the expansion of this graph by in turn thinking of flows in this graph. So this inequality in the other direction, it's saying that if you have a lower bound on conductance, that also gives you a lower bound on lambda 2, and so it gives you an upper bound on the mixing time. In fact, many MCMC algorithms are analyzed by bounding the conductance of these exponentially big graphs. Okay. So all this suggests that it would also be quite interesting to see what is a robust version, not just of the fact that lambda 2 is 0 if and only if the graph is disconnected, but also of the more general fact that lambda k is 0 if and only if the graph has k or more quantity components. So James Lee and Cheyenne Ovesgaran and I thought about this problem, and what we proved is the following connection, that it's a characterization that lambda k can be small if and only if your graph has k or more disjoint sets, each one having small conductance. Okay. So for k equal 2, this is say there is some cut of small conductance, but for every k you have a if and only if connection of this form. So this is what it means for a graph to have small lambda k. So we can capture this with a precise definition. We can call the order k conductance to be the solution of this min-max problem. Notice it looks a bit like the min-max definition of lambda k. So this is the minimum over k disjoint sets of whatever is the conductance of the worst set. Okay. So this quantity is small if and only if you can find k disjoint sets, each of small conductance. Now this quantity is 0 if and only if the graph has k quantity components or more, because it means that you can find k disjoint sets with no outgoing edge. So let me give you some example of how this works. For example, the order 3 conductance of this graph is very large, even though the graph is disconnected. So this is a graph with 0 order 2 conductance, but pretty large order 3 conductance. While this is a graph where the conductances of every small orders are small, you can not just find 2 non-expanding sets, but 3, 4, or more. And our precise relationship is like this. The lower bound is the same as for the case k equal 2. Just looking at the min-max definition of lambda k, just a relaxation of the order k conductance. And the upper bound is constructive. So we show that if you're given the eigenvectors of lambda 1 up to lambda k, and lambda k is small, we can find the k disjoint sets that witness the fact that the order k expansion is small. So this is also an approximation algorithm for order k expansion, in the same way that Fiedler's algorithm is an approximation algorithm for conductance. Okay. Now, in terms of the upper bound, if you are willing to find, if you still find it interesting to find somewhat fewer sets that are guaranteed to exist by the lambda, like say you know that lambda 10 is small, but you just want to find 6 or 7 non-expanding sets. Maybe lambda 100 is small, but you just want to find 50 or 60 non-expanding sets. Then the extra loss compared to the square root of lambda k, instead of being polynomial in k, it's logarithmic in k, and this is known to be tight, and it was also proved by Luis Raghavendra, Tetali, and Vempala with a slightly different algorithm. And we don't know whether this polynomial factor here is tight or not. So it could be that it's some kind of jump in difficulty in going from a tight result to something where you find somewhat fewer sets, but it could just be that we don't have the right algorithm yet. Now the reason why we thought that this result was interesting is that somehow this is to certain spectral algorithms that are used in practice, sort of as the Cheeger inequality is to Fiedler's algorithm, in the sense that it, although not completely, but so it begins to give some rigorous explanation for why they work well. So the way clustering of graphs, especially graphs that encode similarity between pairs of objects, is done, is to compute the eigenvectors of the sum of the smallest eigenvalues of the Laplacian. So this could go between 5 and 80 depending on the applications. K would be somewhere between 5 and 80. And then you compute this embedding, where exactly as I described before in the case lambda k equals 0. So you're given maybe 5 eigenvectors, and then you use them to map every vertex to a 5-dimensional space. So every eigenvector gives you a number, so together they give you a k-tuple, and this will be the mapping of vertices in space. After that, those algorithms forget about the graph and just try to cluster those points in space using geometric algorithms. Usually they apply k-means.
You don't mean the same k, right?
What's that?
You don't mean the same k.
It doesn't have to be the same k, although often they use the same k. So this is known to work well in various random models, and here is how things work in a specific random model. So this is a graph of about like 110 vertices, and the way I generated it was to divide the vertices into 3 subsets and then put edges with higher probability inside each subset and with lower probability between subsets. So it's some kind of planted tree partition of the graph. So various generative models of kind of data of different types have similarity relationships of this form. Okay, then I computed the eigenvectors of the 3 smallest eigenvalues of the graph. This gave a mapping of the graph in 3-dimensional space. But actually, 1 dimension is always kind of trivial. It gives you a constant, the same constant for each vertex. So whenever you do this for some value of k, you actually get a k minus 1-dimensional embedding. 1 dimension gives no information. So it looks like this. And the colors represent the partition unknown to the algorithm that I started from when I drew the random graph. And this embedding really packs the vertices that the generative model would like to be in the same cluster together. And essentially any geometric clustering algorithm, maybe with a couple of outliers, will figure out what the 3 clusters are. So those kind of things were known before, but what was not known is what kind of behavior on what can be rigorously said about non-random graphs. So both our algorithm and the algorithm of Luis Raghavendra, Tetali, and Vempala, they have a rigorous guarantee. So if it is possible to find a certain number of non-expanding sets, the algorithm will find them. The algorithm starts from exactly that embedding. We don't apply k-means or anything that is so simple to explain, but we do forget about the graph and just apply some kind of geometric clustering. So what we do is to partition the space randomly and then patch together those random regions. But overall, it does justify the fact that in every graph, not just in random graphs, this embedding gives information that is useful for clustering. Okay. Now, coming back to the am I out of time?
No, we have 19 minutes.
Okay. Oh, so it's until 5:30, not until 5. Okay. No, I've careful what you wish for. So going back to the k equal 2 case, so this is the 1980s Alon-Millman Cheeger inequality. So this is a bound with this quadratic gap, and both sides are tight. Like there are graphs for which the conductance is lambda 2 over 2. There are graphs where the conductance is roughly the square root of lambda 2. But what we proved with what Cheyenne, Ovesgaran, and this Hong Kong group proved last year is that at least for some graphs, you can prove an upper bound, which also holds for the output of the simple algorithm, which is linear or so somewhat better than lambda 2. So what we prove is that when you look at the quality of the cut found by that algorithm that takes the eigenvector of lambda 2, sorts the vertices, and then looks at the n-1 cuts that you get by taking an initial segment. Well, in the worst case, this will be something like square root of lambda 2. But it's also true that for every k, the expansion that you find is at most an absolute constant, something like 7, times k divided by the square root of lambda k. So for k equal 2, you just get the same that you get here, maybe with a worse constant. But if you have a graph where the spectrum has a gap, so where maybe lambda 2 is small, but lambda 5 is very large, well then this is a considerably better upper bound. Now graphs that come out of generative models, where you say there is some unknown partition, and then edges are random and have high probability inside cluster and low probability between clusters, are graphs where if you start off with k clusters, lambda k plus 1 would be large. So graphs that come from standard generative models, they will be graphs where this bound is much better than this bound. Of course, we already know that in those graphs, spectral methods work very well. But this is a worst case analysis, something that says, so here it's a specific parameter, okay, so the minimum over k of k over root lambda k, and in every graph in which this parameter is large, the Fiedler algorithm will work very well.
Luca, are we still working with the Laplacian spectrum?
Yes.
So lambda k can be at most 2. How much better?
But lambda 2 can be very small.
Sure,
So,
but the root lambda k.
so you have a big difference between the root of lambda 2 and lambda 2 itself.
I'm sorry, Nadia, what's...
No, if we are in the same ballpark, then lambda k can be at most 2. Yeah. So the most the denominator can value is a factor of 1 over root 2, right?
Yeah,
Oh, no. So imagine...
It's the square root, the main thing, so... Gotcha. Okay.
Yep.
It's the square root of the lambda 2 that really makes the difference. It's not the lambda k, but the lambda 2, which is square root or not, right? That's the issue.
Yeah, I mean, one way to see it is that in this algorithm, the approximation ratio, like how much worse than the optimum you are, is 1 over root lambda 2. In this algorithm, it's k over root lambda k. So you could have graphs where lambda 2 is very small, but those are the graphs in which you want to apply this algorithm because you want to find the sparse cut. So that 1 over root lambda 2 error will be a very big number. But such graphs could also be such that maybe lambda 7 is 0.1 or 1, and then this bound will give you a constant factor approximation. So in general, this sort of mean over k of k over root lambda k, you can think of it as some kind of graph parameter. In some cases, it's not something very good, but in some cases, something very good. And in particular, it explains the behavior of some random models. So this will be, in general, the approximation ratio of the sweep algorithm. And the important, so one thing to notice here is that the algorithm does not know k, does not know lambda k, does not know the eigenvectors of lambda k, it just knows the eigenvector of lambda 2. So these properties of the spectrum of the graph, they come up in the analysis, not in the algorithm. The algorithm is completely oblivious to all this.
Is this for every fixed k or for every k?
This is for every k, although for very large k you get diminishing returns because it also appears in the approximation error. So I'll tell you something about the proof of this result. It comes in two parts. The first part is a structural result about graphs where lambda 2 is small and lambda k is large, graphs where there is this kind of spectral gap. And what we show is that in this kind of graphs, the eigenvector of lambda 2 is sort of almost Boolean. So it's such that when you look at the entries, there are 2k values such that most entries are close to those 2k values. Another way of thinking of this is that if you think of a vector as a way of mapping vertices to real numbers. So each vector x of this form can be seen as a way of putting the vertices of a graph on the real line. So then the Fiedler algorithm will just be some way of partitioning the vertices by breaking up the real line at some point. So this is saying that in graphs where lambda 2 is small but lambda k is large, when you do this mapping using the eigenvector of lambda 2, the vertices will not look like all over the place. They will look clustered into k places, or 2k places. So for example, in the case of the cycle, when you take the eigenvector of lambda 2 of the cycle, that will spread the vertices uniformly. And in fact, the cycle is one of the cases where the Cheeger inequality is tight for the upper bound. But if you have a graph that is like two expanders and then some edges in between, lambda 3 will be very large. And when you look at what this embedding looks like, the vertices corresponding to the two expanders will concentrate in two tiny regions far apart. And sort of this shows that some kind of clustering of the values of the entries of the eigenvector is necessary for all graphs where there is a gap between lambda 2 and lambda k. And the other result says that in every graph where the eigenvector of lambda 2 looks like this, you have an improved analysis of the Fiedler's algorithm. Something that it's order of k times lambda 2 plus an error term that depends on how good of an approximation you have of your eigenvector in terms of a vector that has only k or 2k distinct values in the entries. Yeah. So combining those two, we get our upper bound. And we'll say a couple of things about each of the two steps. Okay. So here, this number r of x, maybe I have a definition. It's that expression that you minimize when you find eigenvalues. So r of x is that expression summation over the edges uv of xu minus xv squared divided by the norm of x. So this is what we prove in general. So let's see how to argue the case in which lambda 2 is 0. So this vector x has a Rayleigh quotient of 0. But also the ratio is well defined, so lambda k is positive. Well, in this case, the vector x has to be constant on kinetic components. That's the very first observation we made when talking about those expressions. But if lambda k is positive, G can have at most k kinetic components, or maybe k minus 1 even. Yeah, less than k, so at most k minus 1. And so that means that the vector x itself, if it's constant on kinetic components and there are only k minus 1 kinetic components, it's a vector that has the entries ranging over no more than k minus 1 distinct values. So in this case, x is a distance 0 from a vector y that has less than 2k distinct values in the entries. So this is a simple observation, and our result is sort of a robust version of this. Something that says that whenever lambda k is much bigger than the Rayleigh quotient of x, x must be clustering vertices into 2k values. And in fact, the way we argue it's more like a contrapositive. So we look at the way a vector x embeds vertices on the line, and then we try to find the best clustering of those points on the line. And if it's a very good clustering, that's already a witness that x mostly has only 2k distinct values in its entries, because we found the centers of those 2k clusters will be values such that most vertices, which means most entries of the vector, have values close to those 2k values. Now, if we cannot find a good cluster, then we find the witness that lambda k has to be small. So this part is a bit more technical, but the point is that we can find in this embedding so k regions where the points are kind of even in the best cluster, the points will be kind of spread in each region, not close to the center. And so we can kind of restrict, we can sort of, for each of those regions, we can zero out the vertices not in that region and get something with a comparable Rayleigh quotient. And this will give us k vectors that are non-zero for disjoint subset of vertices, and each of them has a small Rayleigh quotient. And that's a witness that lambda k is small. So there is a bit of technical work here that it's difficult to summarize in a few sentences, but that's the general structure of the argument.
So what is, so 2k here is some constant times k?
Yeah. So the only reason is that not every region might necessarily give a vector with good Rayleigh quotient, but the average region does. So then one can have a Markov argument that says, well, then 90% of the regions will give something that is no worse than 10 times the average. So it doesn't have to be 2. It can be any constant larger than 1, and that will show up in a loss in the constant. For the second result, maybe one thing I can tell you is, again, kind of what would be the extreme case where this distance from x and an approximation by a vector that has only 2k distinct entries, the case in which this distance is 0, so x itself has only k distinct entries. So in this case, it's known that the algorithm, the sweep algorithm, only loses a factor of k, which is sort of what's happening here. And when this distance is a constant, we know that things are never worse than the Cheeger inequality that gives you a square root. And so the way we prove this is some kind of mixing of the arguments that give an upper bound of k when there are only k distinct values, and the argument that gives the Cheeger inequality if you don't know anything. And so that's the way the two things balance. And pretty much everything is tight also here, so that's the right bound. So there's one more sort of extremal result of which it's interesting to think about a approximate version, which is the fact that if you know that, say, lambda k is 0, and lambda k plus 1 is positive, so that means that your graph has exactly k quantity components. So the graph can be broken up into k subset of vertices. Each subset of vertices has no outgoing edge, but also each subset of vertices induces a connected subgraph. So the way you like to think of this as a robust version would be that the robust version of a set of vertices being disconnected from a set of the graph is that that set of vertices has small conductance. And the robust version of a set of vertices inducing a connected graph is that you have a set of vertices that induces an expander. So what you want to say is something that if lambda k is small, but lambda k plus 1 is large, then you can find k sets of vertices that partition the graph. Each of them in the whole graph has small expansion, so there's few outgoing edges. But each one, if you just look at the induced subgraph, is an expanding graph. So that gives you a very nice structure for the graph. It says your graph is made of k expanders and then not too many other edges. So Tanaka proved the bound of this form. It uses our result about lambda k being small, implying that there are k non-expanding sets. And so he proved that if you have at least this separation between lambda k plus 1, so some kind of quadratic gap plus something exponential in k, then you have a result of this form. You have k sets, each one in the whole graph has a conductance that depends on lambda k, and each one induces a subgraph whose expansion depends on lambda k plus 1. But his proof is non-algorithmic. So he really needs at some point in the argument to say, okay, here is a graph, let's take the least expanding cut of this graph, which is an NP-hard problem, and then do something. So what we proved with Cheyenne last year was that if you reason not in terms of lambda k, but in terms of these order k conductance parameters, you just need an arbitrarily small gap, and you can get non-constructively this kind of conclusion. And if you have a gap in the, but so this, you cannot certify, you cannot compute, and also the partition is non-constructive. But if you have a gap that is, so this quadratic gap between eigenvalues, but then only something polynomial in k instead of exponential in k, then the partition also exists and can be found algorithmically. So for what's interesting about the first result is that it's so S star is can be this order k conductance only needs to increase a little bit to get some structured theorem. For the second part, it's something that is algorithmic and polynomial in k instead of the previous result that was exponential in k and non-constructive. What's that? Okay, that's probably the second to last slide. So now there's been a lot of work now. So I'll just mention without getting into the specific results. There's been a lot of work showing that when a graph is such that lambda k is large, many problems that are hard to approximate in general, they seem to become considerably easier. In particular, you can get very good approximations for various problems like constraint satisfaction, conductance, and so on, in time that is exponential in this parameter k. The improved Cheeger inequality that I mentioned before, it sort of shows that even the simple Fiedler algorithm works better when lambda k is large. It doesn't have to be exponential in k. But then the approximation here is not as good as the approximations that they get here. And something else I proved with Cheyenne Ovesgaran recently is that the analysis of the Arora-Rao-Vazirani algorithm for conductance and sparsest cut can be improved in graphs where lambda k is large. You get an approximation that is square root of lambda k, sorry, square root of log k instead of an approximation of square root of log n. So again, it's sort of never worse and sometimes better. Here they get constant factor approximation for every k, but then the running time is exponential in k. Roughly, the idea is that graphs where lambda k is large, they do look like k expanders plus some extra edges. And in many problems, you don't want to separate the vertices in each of those expanders. So you just need to know how to group them. So you can do them by brute force in time to do the k, but you can also imagine that each of them is just one vertex, and then if you add a root log n algorithm for general graphs, this becomes a root log k algorithm. So that's not literally how those arguments work, because some of the way we know to argue that when lambda k is large, the graph looks like k expanders, those results lose. They're too weak to actually imply that you can just say, I don't never want to split one of those expanders. But they're sort of the moral underneath. There are reasons why you might expect those results to be true. That roughly speaking, the intuition about the cases in which lambda k is large would suggest that those graphs look like they only have k vertices. So among things you can do in graphs with k vertices is to get ARV to have approximation root log k and brute force to run in time to do the k. So here is a problem, so not fully specified, but I think it's very interesting, is that in the analysis of the simple algorithm based on sorting the vertices, so we have this upper bound and lower bound, and our improved analysis comes from an improved upper bound for graphs in which lambda k is large. But one could get an improved analysis potentially also by showing that an improved lower bound, that somehow if you have a graph in which you can prove that lambda 2 is much smaller than the expansion, the fact that you get a cut in polynomial time of expansion square root of lambda 2, well, that could be a cut of expansion much less than square root of the expansion. Is somehow you know that lambda 2 is much less than the expansion. And this is sort of what happens in the planar separator theorem of Spielmann and Tang, what they show is that in planar graphs, lambda 2 is always small. And so that implies that the simple algorithm always finds a cut of expansion at most 1 over root n. But this is not saying that in planar graphs there is some constant approximation or a kind of worst case approximation. It just says there is a non-trivial upper bound on the quality of the solution. But if we could find some interesting class of graphs for which we could prove that lambda 2 is always much smaller than the expansion, then automatically for those graphs we would have an improved approximation. In fact, if you could argue that for some class of graphs lambda 2 is always quadratic in the expansion, then for those graphs you could get constant factor approximation. I mean, presumably this would be kind of too much to ask, but maybe you could say in this class of graphs either lambda 2 has to be much smaller than the expansion, or there is some other recognizable property that allows some other algorithm to do well. So that's something that I would consider promising, and I've never seen something like that in any algorithm. Okay. So I will stop here. I'll give you a link to many short expositions about expanders that I've written in the last couple of years. Thank you.
Thank you. Any questions? Well, Tiger, there we go.
So another thing where eigenvalues are pretty good in the random case is to find the coloring. But to this there is no analog in worst case, right? Probably it would not mean to approximate the chromatic number, but to find a near coloring where there are only a small number of edges that violate it.
That's right. So you might imagine that looking at the k largest eigenvalues of the Laplacian and then taking that embedding, at least in random graphs, would push the color classes together, and yeah, in general, it should give some kind of approximation. I mean, this would only be weaker than the semi-definite relaxation of coloring, but yeah, maybe there is something interesting to prove about the embedding using the k largest eigenvalues, that some coloring-like problem gives some good approximation. So.
by the way,